Hello, welcome to another Stat 510 video. In this video, we're going to talk about convergence of random variables, um, otherwise known as large sample theory or asymptotics. But essentially, the question we want to ask is, what happens with more data? So, we always say, oh, more data, we want more data, we want more data. Well, so something we'd like is for our statistics to have more good and understandable properties as we acquire more and more data. So that's what we're going to talk about in this video. So there's going to be two sort of main ideas that we are building towards and discussing in this video. The first is the law of large numbers, which is essentially going to tell us that with high probability, the sample mean is close to the true mean. The other big idea that we're going to talk about is the central limit theorem. This essentially says the sample mean is approximately normal. Now, everything I just said is not true in general. When is it true? Well, it's true when n is large. Now I'm going to put large in quotations there because what large is dependent on certain things. So somewhere it's possible, and this is no one's fault, but you may have taken a probability and statistics course where someone said something like, oh, hey, if n is 30, the central limit theorem applies. I just want to caution that that's not true. That's often true in those courses for the sake of, checking your understanding of the idea and with maybe some of the nice distributions you're using there, but that is not true in general. I can't tell you any particular n. All I can do is wave my hands and do scare quotes and say large, but we'll mention more about that in a little bit. Okay, so first we need to define some notions of convergence, and I'm going to try to adjust my camera a little bit here so that I can stay on the screen but not be in the way. Okay, hopefully that'll work. All right, so first, a definition. So we have a sequence of random variables x1, x2, x3, and so on and so forth, and some other random variable that we'll just call x. So we want to define this notion of what we call convergence in probability. So we want to say this sequence of random variables converges to this other random variable. And we have some notation for this. We would say that x sub n converges in probability to x. So this is the case if, for some epsilon, this probability here goes to 0 as n goes to infinity. And essentially this probability is looking at the absolute difference between xn and x being bigger than some arbitrarily small value. That has to go to 0 as n goes to infinity. Okay. So another definition we're going to need is something called convergence in distribution. So now we're also going to introduce the CDFs of both the sequence x sub n. So f sub n is the CDF of xn, and f is the CDF of x. So then we say xn, that sequence, converges in distribution to x. We write that like this. One note here is that this notation is slightly different than the book's notation, just because I'm not good at drawing that squiggly arrow the way they do. So I'm using an arrow with a D above it. And I'm using a lowercase d, so because the uppercase D would probably look like a P. But anyway, so this convergence of distribution happens if the limit of that one CDF, f sub n, is exactly f, the CDF of x. With one note, for t where f is continuous. So we only need this limit to be f of t for t where f is continuous. And that'll come up in a second. Okay, so one minor note here is that sometimes when we're dealing with what we call point mass distribution, meaning the random variable can only take one possible value and it always takes that value, so with probability 1. So if we had a sequence of random variables to converge to this random variable, either in probability or distribution, we would sometimes instead write this like this, saying that it converges exactly to that value. Okay, that's kind of just a minor notational thing. Okay, now let's talk about an example that'll hopefully help us understand what's going on with these two notions of convergence. So here we're going to have x sub n be a sequence of random variables that are normal with mean 0 and variance 1 over n. So essentially, as we move along in the sequence, the variance gets smaller. So hopefully, you have some notion of, well, the distribution is getting smashed closer and closer and closer to being almost a point mass around 0. So basically, there's some notion of convergence to 0 here. So the question we sort of want to ask is, does xn converge to 0? And we want to ask that question for both in distribution and in probability. So first we'll do distribution. So does x sub n converge to 0 in distribution? So first, I've written out here the CDF for a point mass at 0. So for any value less than 0, the CDF is 0. And then once we cross 0, the CDF jumps up to 1. And then for everything greater than 0, it's still 1. Another thing I've done here is I've defined a new random variable z, which is the square root of n times x sub n. And essentially what I've done there is I've standardized x sub n. Okay, so now I want to look at the CDF of x sub n. So, and we're going to split it up into 3 cases eventually, 2 for now. So when t is less than 0, that CDF is, just by definition, what we see here. I'm going to pause for just a second. Apparently, I can't pause. Okay, I'm back. You may have heard me stuttering there. I didn't know if it was paused or not. Okay, but I think we're paused. I was paused, and now we're back live. Okay, so right, I was talking about the case where t is less than 0. We have the CDF here just by definition, and then what I'm going to do is I'm going to multiply by square root of n on both sides there, so kind of like this. So square root of n x sub n less than or equal to the square root of n t. Okay, and then we said that square root of n times xn is standard normal. So this is the probability that a standard normal random variable is less than or equal to square root of n times t. Okay, so it should be clear then that this quantity goes to 0 as n goes to infinity. And why is that? Because remember, t here is less than 0. So square root of n times t is going to be a negative quantity. And the more and more and more negative we make it, but just by definition of CDFs, this is going to have to go to 0. Okay, and so hopefully you can see when we flip this then and have t greater than 0, I've sort of skipped some steps already, but we can clearly see that this goes to 1 then. And I can actually conclude here now. So now I can go ahead and say, well, f sub n of t goes to f of t for t not equal to 0, because we haven't considered that case. But even with that, then x sub n does indeed converge in distribution to 0. So why can I just ignore t equal to 0, like I've done here, well, when t is 0, what do we have? So f sub n of 0 is 1/2. Because again, remember, x sub n is a normal random variable with mean 0, so the probability of less than or equal to 0 is exactly 1/2. But this is not equal to f of 0, which is 1. So we see that these are not equal, but we don't care because x, 0 is exactly the discontinuity point, right? So we said we needed for all t where f is continuous, but f here is certainly not continuous at 0. So we don't need to worry about that. Okay, so we have convergence in distribution. Do we have xn? Again, this is what we're looking at. Do we have this in probability? So we will appeal to Chebyshev's in a second here. Or no, with Markov's. Well, kind of both. But anyway, so note that what I have written here, this is actually x sub n minus 0. But, when you subtract 0. But I'm just writing this to note that it'll, I think, help us better relate back to this, because 0 here would be the random variable x that we're trying to converge to. Okay. Right. So what can I do now? So I'm going to go ahead and square both sides here. So we have the probability that xn squared is greater than epsilon squared. Okay. And now I use Markov's. So we get less than or equal to the expected value of, I'm just going to say x sub n squared, because again, with the square, the absolute value doesn't really matter. And then epsilon squared. Okay, and then, well, because this has mean 0, the expected value of xn squared is exactly the variance of x sub n. And again, we have divided by epsilon squared. And so this is then what? So the variance of x sub n is 1 over n. That whole thing divided by epsilon squared. And if we let n go to infinity, then this goes to 0. So we have x sub n converges in probability to 0. Okay. So the thing to... one of the natural questions is, well, what's then the difference between convergence in distribution and convergence in probability? So we've seen the definitions and we've checked these things, but what is the intuitive sort of difference between these things? So to talk about this, I want to first note that convergence in distribution does not imply convergence in probability. We'll talk about the reverse in a little bit. But so what that means is I should be able to find an example where we have convergence in distribution, but not convergence in probability. And that's what we're going to talk about here. But I think I'm going to need to move myself. Okay. So here I have an example where x, the variable that we want to converge to, is standard normal. And I'm going to say that x sub n is equal to negative x for n is 1, 2, 3, blah, 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 all the possible n, right? So let's first talk about the distribution of negative x. So it's just a transformation of the distribution of x. So the expected value of negative x, which I'm going to actually denote as x sub n, because they're equal, that's what we're talking about. So this should be minus 1, the coefficient there, times 0, so that's 0. And the variance of x sub n is what? Negative 1 squared times 1, so that's 1. So that means the distribution of negative x is normal 0, 1. because when you transform a normal random variable, if it has the, all you have to do is find the new parameters, and the new parameters here are the same as the old parameters, so it's also standard normal. So that means that in this case, the convergence is kind of trivial here for in distribution, because x and x sub n, they have the same distribution. But I want to be really clear here. They have the same distribution, but they are not the same random variable, and that's going to be very important here. And just to be clear, so because of the same distribution, the limit here, this is as n goes to infinity, is exactly the CDF of x, and we can say that x sub n converges in distribution to x. Okay, so a really silly example, kind of, but this is true. So xn converges to x in distribution. And again, one step further, xn and x actually just have the same distribution for any n. Now, what about in probability, right? So here I've written out the probability statement that we need, but let's think about this right away, right? So xn is literally defined to be the negative of x. So if I randomly sample from x and it is 3, well, that means x sub n is negative 3. So right away, that should tell us that we're going to run into a problem here. So and again, so x sub n here is defined to be negative x, right? So this becomes the probability that the absolute value of 2x, the negative goes away because of the absolute value, greater than epsilon. So this is the probability that the absolute value of x is bigger than epsilon over 2. So again, this is the probability that the absolute value of a standard normal random variable is bigger than some arbitrary value. Well, clearly, this is not equal to 0. And there's no n here, so it's not going to go to 0 as n goes to infinity. So we do not have convergence in probability here. So the thing that this is hopefully highlighting is that convergence in distribution only cares about the distribution. So it says, do these two random variables have the same distribution in a limiting sense? So as n goes to infinity. So does one's CDF converge to the others, right? So they only care about the distribution. And again, if you have a random variable that's like a nice symmetric around 0 and take a negative of it, well, it's the same distribution. But convergence and probability cares about the question. So another way to say it is, let's say I have these two random variables and I take a random observation from both. Are they going to be very close to each other, right? And that's why we fail here, right? Because no matter what we sample from one, the other one is clearly far away because it's defined to be the negative of the other. So convergence and distribution cares about the distribution. Convergence and probability cares about sampling from both those distributions, and are the, probabilistically, are those two observations going to be close together? That's sort of the key difference. Okay, so a brief aside here to say we can define another notion of convergence, which is convergence in quadratic mean, which we would write like this. Nothing too fancy there. And here we have the condition we need to claim that xn converges in quadratic mean to x. So why do I mention this? So sometimes if you have a stronger form of convergence, it implies a weaker form of convergence. So for example, if you have convergence in quadratic mean, that automatically gives you convergence in probability. And sometimes this condition is just easier to work with than the probability statement from convergence in probability. The reverse of the example we were just talking about is if you have convergence in probability, you get convergence in distribution. And I don't know why I did a capital D there. That's not helpful because it looks like a P, so like that. Now, there is one particular case where if you have convergence in distribution, you get convergence in probability. And that is for a point mass distribution. So if you have a point mass distribution and you prove that it converges in distribution, then you get a convergence in probability. But aside from that case, so for the first two cases, the reverses are not true in general. Reverse is not true. So for example, if you have convergence in probability, you can't assume that you have convergence in quadratic mean. It could be that both are the case, but you can't just say, well, because I have convergence in probability, I have convergence in quadratic mean. That doesn't work in general. Okay, so a lot of text on this page. So now I want to talk about how we can sort of combine. So we have, let's say, random variables x and random variables y, and sequences of random variables xn and sequences of random variables yn, and we also have a continuous function g. So looking at the first bullet point here, so let's say that xn converges in probability to x, yn converges in probability to y. Well, then we can say that the new random variable sequence xn plus yn, that converges in probability to x plus y. And then we have a whole list of similar concepts here. I want to give a name to some of these. So these last two, these are the continuous mapping theorem. So whether or not we're talking about probability or distribution, if you have a sequence converging, but then if you apply a function to that sequence, it'll converge to the thing that the original thing converges to, but the function of it. Okay, I did not sequence those words necessarily correctly, but hopefully you get the idea. And then this and this. So these have to deal with either adding or multiplying by something that converges to a point mass. This is called Slutsky's theorem. Okay, but in generally, these can be useful notions for arriving at the things on the right-hand side, given the things on the left-hand side. That's just how that works. Okay. Didn't actually have that much to say there. Okay, so now moving towards one of the big ideas. So there's this thing called the law of large numbers. There's a couple different formulations of it. We're looking at what we call the weak law of large numbers here. So we have a sequence of random variables, x1, x2, xn. They are IID, and we're going to denote their mean by mu. When this is the case, we can say that x bar sub n, so that is the sample mean, converges in probability to mu. In other words, when n is really large, the distance between the sample mean and the true mean should not be very far from one another. Okay, so for the proof, we're going to be a little bit lazy and add a condition and assume that is we have finite variance. We could prove this without that, but it's too much work. But so here we have the probability statement that we need to go to 0 as n goes to infinity. We can directly head to Chebyshev's here. And so we're going to bound this above by the variance divided by epsilon squared. Again, that's due to Chebyshev's. And then so this is sigma squared over n, because again, that is the variance of the sample mean. And then epsilon squared here. And then we can pretty clearly see that for a finite variance, as n goes to infinity, this is going to go to 0. I realize you can't see that, but I think, it's just 0. That shouldn't be a big deal. Okay, so that proves the weak law of large numbers. Okay, but again, so sample mean converges to true mean. In other words, for large n, the probability that the sample mean and the sorry, I lost my train of thought there. Sample mean close to true mean with large sample. Okay. Moving on. Central limit theorem. So central, I always forget if this is true. Central here refers to the fact that it's like the main limit theorem of all of statistics. That might be a little confusing because it involves the mean and that is a notion of center, but this is the main limit theorem. I'm gonna mention that this is what's called the classical central limit theorem. So basically, there are different versions of the central limit theorem that have different conditions on it. So these conditions here are actually stronger than what we need, but this is the sort of the most classic statement of the central limit theorem. But we could relax these conditions a little bit, but these are just the easiest to work with and talk about. I would note too that we're not going to prove this in this video. I'm going to prove it in a whole separate video because it's a whole diversion from what we're talking about at the moment, but we will prove this. So in this formulation of the central limit theorem, we have x1 through xn that are IID random variables with mean, mu, and finite variance sigma squared. And we have our usual definition of the sample mean. Okay, so under that setup, if we sort of what we call standardize the sample mean, so we subtract off the sample mean's mean and divide by its standard deviation. So that's this resulting thing we have here. So this converges in distribution to z. That is, z is a standard normal 0, 1 random variable. So this is a truly remarkable thing, because what we're saying here is that we have these random variables, and we haven't said anything about their distribution except they have some mean and some variance. So we've ruled out a few classes of distributions, but for all these other distributions, it doesn't matter what distribution it is. If you let n go to infinity, the sample mean is going to converge in distribution to a normal. That's a pretty big deal. So one of the things you can do with the central limit theorem is you can approximate probabilities. So statements of this form, so say the probability that the sample mean is bigger than some quantity, that is now approximately normal. And I want to be optimistic but also cautious here. So two sort of casual statements that might get thrown around here is that for any distribution of the random variables and when n is large. So I just want to caution that this is not true. So it's not for any distribution, it's for any distribution. It's for any distribution that satisfies finite variance as we've defined it here. So if a distribution doesn't have finite variance, you can't apply this theorem. The other thing is that, like I mentioned, is when n is large. So large n is dependent upon what the underlying distribution is. I'm realizing I didn't put this in the homework, but I didn't put it in the spring 2021 homework. Maybe in future semesters I'll go back and do this. If you haven't done it before, it'd be a really good idea to go and do some simulations about the central limit theorem. In particular, looking at differences in how big n needs to be to get something that's approximately normal for various underlying distributions. So you should try something like normal, something like uniform, something like exponential, maybe something like Cauchy, and see what happens there, and see how big you need to make n for the histogram of a bunch of like simulated sample means to look approximately normal. That would be a really good exercise to go through. You can probably search and find a web application of someone that's sort of packaged that up already, but something that I think is really instructive to do that once or twice. Maybe we'll do it on a later homework, but I didn't do it on this one. Anyway, okay, so sometimes we can say a bunch of different things that all mean the same thing. So here are some sort of alternative forms, but I want to be really careful about some of these. So for example, we could say z sub n, again, that's defined here. Well, that's approximately standard normal for large n. We could say that the sample mean is approximately normal with mean, mu, and variance sigma squared over n. I actually want to focus on this for a second. So all these things are largely saying the same thing. So left-hand side is a random variable, right-hand side is its sort of approximate distribution. But so the way we use these is, so if I have a sample mean and I have some arbitrarily large n, I can approximate its distribution by normal distribution with mean mu and variance sigma squared over n. But I want to be a little bit careful. I should not write something like this. So this you really can't say. And why is that? It's because of this n right here. Because, oh, I'm really bad with this. Okay, so this kind of doesn't make sense. Because how can something converge in distribution to a distribution that has a divided by n in it when n is going to infinity? Because then that would have collapsed this distribution down to a point mass at mu, and that's not the case. So the things on the left-hand side of the screen are approximate distributions given what we know about the central limit theorem for a large but still finite n. But to actually talk about a notion of convergence and distribution, you're going to need to look at something like this, where the n is on the left-hand side. You're not converging to something with an over n in it, because that just doesn't make sense. Okay. Right. So something you might realize about this formulation of the central limit theorem is that often in practice we don't know sigma. So we can replace sigma with S sub n, that is the sample standard deviation, and we still then get convergence and distribution. And I'm going to claim proof by exercise, meaning this is on the homework. Not particularly difficult if you think back a few slides. I guess the hint, I'll give a hint. Think about the quantity S sub n squared, and maybe think about limiting notions of this quantity here. Maybe what does this converge to? Think about that. That'll be a helpful hint, I think. Okay, so something we sort of mentioned is, when n is large, x sub n, for example, x bar n, so the sample mean is, close to a normal distribution. But how close? So there's actually a theorem about this. So given some condition here on the moments of the underlying distribution, we can bound the difference between, so this would be the CDF of z sub n, and this is the CDF of z, an actual standard normal. So we can bound the sort of maximal distance between these two CDFs at across all possible input values z by this quantity here, and note that it has an n in it. So we're not talking about necessarily what happens asymptotically, but for a finite but very large n, how far apart is the true distribution of Zn and the standard normal that we think that it's converging to. So this might be a good thing to maybe try out some simulations about, to see just how far apart those are, because it's kind of hard to get a sense of what this quantity on the right hand side actually is and how far away that could be. But this might be something to do some computational checking to sort of strengthen your intuitions there. Okay, so lastly, just a quick note about the delta method. So suppose we have some random variable y sub n that we can, do the usual standardization and then say it converges in distribution to normal 0, 1. So perhaps we use the central limit theorem to get that. And g is a differentiable function, and the derivative of that function at mu is not 0. Then this new quantity I have written here this converges in distribute. Oh, that's not how you write that. That's not how you write that. Converges in distribution to a normal 0, 1. So what does this do for us? Well, essentially then, if we have some random variable that is approximately normal, mean mu, variance, sigma squared over n, then if we apply that function g to that random variable, well, this new random variable is also approximately normal with these new parameters that that are functions of this function g that we introduced. Okay, and there'll be some exercises you have to do to sort of use this, but basically, if you have a random variable that is approximately normal and you apply a function to it, well, the new random variable is also normal. Who would have thought? Common thing. If you have a normal and you do stuff to it, a lot of times you get a normal again. That's a common theme in statistics. Okay, so that's it for notions of convergence. In the next video, we'll prove the central limit theorem just because this video is kind of long and that would have been a diversion. As always, if you made it to the end of the video, good job, and I will see you in the next one.